Hello and welcome to our poster comparing representations that support objects seen in face recognition using deepnet trajectory analysis. Objects seen in faces seem to be comprised of different kinds of visual features. In this project, we are interested in the kind of representations that are needed to support objects seen in face recognition, and in particular, whether these representations depend on more distinctive versus common feature spaces. And for this, we are using comparative deepnet analysis. The reason why we use deep neural networks in this case is because neural networks, given a certain stimulus input and a certain task, like categorization, learn the kind of features that are necessary to support the task. So for this approach, we first trained 3 AlexNets, one on objects, one on scenes, and one on faces. So by training these 3 networks, they have learned the features that are necessary to support objects seen in face recognition independently. To get a sense of whether they learned more similar or different features, we're going to measure the responses of each unit of each layer to a common test set. This test set consists of a mixture of objects, scenes, and faces, all taken from the validation sets. Then with these responses, we can create representational dissimilarity matrices for each layer. Here you can see schematically RDMs for the first couple of layers. Once we have RDMs for each layer, we can correlate each layer with all of the other layers, which gives us this large second-order Uber RDM. So here, for example, this little square would represent how similar layer 2 of the scene stimulus domain is to layer 1 of the object stimulus domain. And you can see the more saturated colors in the diagonal represent the within stimulus domain layer comparisons, and these mixtures of colors represent the between stimulus domain layer comparisons. So this Uber RDM gives us a similarity structure of all of the learned geometries of all layers at the same time. To make sure this is reliable, we repeat the whole process for 10 different test sets. So this is what a Uber RDM for one of the test sets looks like. Darker colors represent smaller distances and lighter colors represent larger distances. You can see that each of the stimulus domains consists of 21 representational stages. So each of these subsquares within this Uber RDM is a 21 by 21 square. However, it's a bit difficult to understand the structure from this kind of visualization. That's why we use multidimensional scaling to plot the distances from this Uber RDM in 2-dimensional space. Each black dot represents a convolution. So we start with conv1 down here, go to conv2, then 3, 4, 5, respectively for the other networks as well. So what this MDS plot shows us is the representational trajectories these networks take from input to output stages. And as you know, we repeated this process for 10 different test sets. You can see here that the variance between the test sets is not very large. So even though the networks were trained on 3 different stimulus domains, you can see that both conv1 and conv2 stages learned quite similar representations before you see any divergence. And what really sticks out here is that networks trained on faces seem to learn more distinctive representational geometries than the ones trained on objects and scenes. We also wanted to see how general our results were. That's why we trained another set of 3 networks, did the whole process again, and compared it to our original results. So on the left you can see our original results, and on the right this is a replication result. As you can see, the 2 are very similar, so this replicated the relationship that we found quite nicely. We also wanted to see what happens if we change the test set that we use. We originally used the mixed test set to allow the representational geometries for all of the stimulus domains to be able to show through. However, this could also cause weird results because the network trained on objects has never seen faces before. So we did the same process again, and this time we used 3 different kinds of test sets, one for objects, one with only objects, one with only scenes, and one with only faces. You can see that this is very similar to the results that we got for the mixed test set. For the places and faces, we can see that the main takeaways stay the same. However, there's some slight rotation, which doesn't really matter because the axes in MDS aren't fixed. Finally, we wanted to know at what point during training this relationship emerges. So plotted down here, we can see the trajectories during different time points during training. One epoch meaning that the network has seen all of the images once. And we can see that the relationship that we find after 200 epochs already emerges after 1 epoch. So even though the features aren't good enough yet to support accurate classification, the relationship between the trajectories is already pretty stable early on, even though the features themselves are still changing. To conclude, we find common feature spaces in early processing stages for object scenes and faces, similarly to how the brain processes visual input along the ventral stream. We also find more distinctive feature spaces for face processing in later stages than for objects in scene stimulus domains. This relationship already emerges after one training epoch, before the network is able to correctly classify anything. Finally, deepnet trajectory analysis can be used as a very general tool for comparing representations learned by different kinds of models, as this provides a relatively intuitive visualization of the representational trajectory taken from the input image across all of the layers to the final representational stages. We could also easily use this to compare different kinds of architectures because the number of layers doesn't matter for this approach. And you can even include comparisons with brain or region representations.